All right. Give them a welcome.
All right. Ray, great to see
Hi.
you.
Yeah.
Please introduce yourself.
Oh, hi. Hi, everyone. So, my name is Ray. I'm from Academy University, Michigan. I am a assistant professor of computer science. So I will teach the parallel and high performance computing next year. So I think it's a good opportunity for me to join this meeting and learn something from you. So
That's
yeah.
fantastic. That's awesome. I'm sorry, which school did you say you were with?
Catherine University.
Oh, okay, in Michigan.
Yes.
Nice. Where is that in Michigan?
In Flint. The
Oh,
city of
okay.
Flint. Yeah.
Very nice. Well, good luck.
All right. Thank
All
you.
right. And is it Weiwei?
Yes, this is Weiwei Stone. I'm from University of Maryland, Eastern Shore. I'm an
Oh, hey.
associate professor in computer science. And for some reason, I didn't the email you sent to me is typed wrong, so I didn't receive the email. So I missed yesterday's meeting. Nice to meet you all, and I will hope I catch up everything today. Thank you.
Yes. And there is on our website that you can see over there, hackhpc.github.io, FacultyHack-Gateways23. I believe the recording from yesterday is going to be posted there. Is that right, Jamie?
Yes.
Okay.
Soon as so I'll get that link from you and I will add it to the site.
Okay, I believe I did share that with you. I'll
Oh.
make sure I share that. I'll double make sure I shared that with you. So great. Let's see who else is new. I think that's all the newbies today. So thank you so much for joining us. Looking forward to getting to know you. One thing you missed out on that we were always talk about yesterday is this Gateways community, this hackathon community, we've been together through everything. We've poured through tears and through successes and through bottlenecks and we've climbed over walls and we've climbed through trenches. We've been through it together for everything.
Yeah.
And you will get to know us as well, and we will go through all of this with you as well. We form a community here. The idea is it's not just one person's idea, it's everybody's idea. And all these ideas spawn into new things and generate new ideas. And this is why this hackathon, this is why this group exists, is to get these ideas to flourish. And you being faculty members, you being professors and teachers, you are that first, shall we say, seed that goes into students' minds and make them think of something brand new, which is why it's perfect for you all to be here today. Hey, Joseph just joined us. Hey, Joseph, I don't think I remember you from yesterday. So, are you new today?
Here. He was here.
Oh, okay. I'm sorry. I must have missed him. I'm sorry about that, Joseph. So great to see you again. Okay. So with that, today is pre-hack training day number 2. All right. So yesterday, if you joined us, there we go. So yesterday we covered the poster template from Dr. K. Thank you so much, Dr. K, for doing that for us. And we had a great overview on GitHub on using it as a repository, using it as a programming environment, and using it as a web server as well. So thank you very much, Jamie, for introducing to all that. Today, we have something kind of cool. I'm really looking forward to it. We have Fernanda Freuter from Voltron Data. First off, I think Voltron Data is a freaking awesome name, especially growing up as a Gen Xer, watching Voltron on TV and playing with the Voltron toys. It's just the next generation. It's a Voltron Data. So looking forward to that, and looking forward to learning more about Fernanda and seeing what you've brought to brought to the HPC world. And then if you look at the schedule, tomorrow we might be doing an overview about SGX3. SGX3 is the sponsor of the conference that we're all going to be going to, the Science Gateways Conference. We'll be presenting our posters that we're creating this faculty hack. And then on Friday, the hackathon kicks off in full gear. We're going to have a special presentation on Project Eureka from our very own HPC.org organizer, Boyd Wilson, who's CEO of Omnibon. And then we're going to do a series of check-ins to make sure that we're progressing, make sure that if there's anything that is that's hindering you, that the organizers can help you and the mentors can help you overcome those. And we'll have a series of check-ins to make sure you're progressing and make sure the hack is successful for you. And then we'll do our final check-in on the 22nd, and we'll have Elijah from Oak Ridge National Labs giving you an overview of their faculty programs that's available to you all. And then the big thing, our grand finale on October 30th at the Science Gateways Conference in Pittsburgh, you all will be presenting your posters. And then also our other organizer, Alex Nolte, who is hackathons is his life, and he will be conducting exit interviews for you all to see how this hackathon went, where you'd like to be able to go, and how we can help you in the future of getting your course implemented. So with that, let me introduce myself. My name is Charlie Day. I am the training and professional development guy here at the Texas Advanced Computing Center, TAC. That's one of our sponsors as well. Let me introduce you to my brother in arms, Jamie.
Hello, my name is Jamie Powell. Let me switch my camera here so you can see me. There I am, kinda, almost. There we go.
There you are.
Hi, everybody. It's good to see you all again. Welcome those that were unable to join us yesterday. We're glad to see you here today, and I'm looking forward to seeing Fernanda's presentation as well.
Yes.
So good luck, everybody.
I would love to work. I would love Voltron to be on my, business card. That'd be the coolest thing ever. The other thing I like to say about Jamie is, if there's ever a true Renaissance man anymore in today's age, it's Jamie. Jamie is the Renaissance man. He does everything and everything on top of that, and multiply that by about 5, and you probably still can't get to all the stuff that Jamie does for us here at the hackhpc.org, as well as what he does for TAC, as well as he does. He's a true ambassador to the HBCUs and to the HBCU cause. And of course, he represents Elizabeth City State University extremely well. So always a pleasure to have you by my side, Jamie. You know that.
Thanks,
and of
man.
course,
I appreciate that.
yep. And of course, our person that everybody has that one keystone, that one first knit that holds everybody together after that. For us, it is Dr. Linda Hayden. She's the one that got this group together. She's the one that planted that first seed that the rest of us kind of grew out of. So, Dr. Hayden, do you have some words for us today before we get started?
I'm very glad to see everybody join us today. Looking forward to hearing Fernanda's presentation and starting our, after we get this pre-hack training out of the way, then we can get going with our hackathon.
Exactly. Looking forward to that.
Yeah.
So thank you so much. So with that, we're going to be doing an HPC overview from Fernanda Froiter. Is that how do you pronounce your last name? I put it into ChatGPT and ChatGPT did not help me.
It's just Porter with an F.
Porter with an F. Okay.
Okay.
Yeah, you want to know what ChatGPT came up with for suggestions on pronunciation of that. So I did, of course, Google you. And honestly, you've done so much. I don't think I could do it justice by doing a proper introduction to you. So I'm going to hand off the floor to you and let you introduce yourself, because you've done a lot in the HPC world, and it's a very impressive resume and background. So I'm gonna hand the floor over to you without any further ado.
Wow, thank you for that introduction. I appreciate that, and I am humbled by that introduction. Basically, my career is a combination of I can't decide what I like doing, and so I keep following things that are interesting to me, and it has worked out so far. So I can't really complain about this process, although it might look from the outside that I have zero direction, but I think if you look at my resume, my direction is basically I like helping people and I like doing cool stuff. That's where I'm at. I started out as a failed computer engineer, and my first class in computer engineering was C++ intermediate programming. And I failed that class, a big old F. And I went crying to my professor's office, and he happened to have his transcript on the wall as a sign to other students who had failed and thought that that was the end of the world. And he says, I too failed, and he pointed to that. So in that spirit, I tell this story to anyone that's ever been and anywhere near computers or wants to make a career of computers. That, you know, failure is an opportunity to learn. I switched to another kind of engineering. I ended up taking C for engineers, and it was a lot of signal processing and data processing. And I was like, oh, I get programming now. This is fun. And so I ended up not thinking that I was a complete failure at computers. I just want to do a mic check. Anyone ever hear me okay? Is the sound good? Great. And so I ended up liking that. And then but I wasn't too keen on electrical engineering. And I took circuits 1, circuits 2. And by the end of circuits 2, I was like, I had enough of circuits. And then I looked at my transcript and I thought, what am I going to do? I really want to work at NASA. That's my goal. I had no idea. I'm the first one to go to college in my family. In fact, my mom didn't graduate high school, so I had no direction at all. I was just like, they told me I needed to go to college. What do I do? So I was attending an HSI institution called Florida International University down in South Florida. And I looked at my transcripts, and it turned out that my favorite classes and the one that had the highest grades on was physics. And every engineering class I had, I kept asking why. Why does a resistor resist? And why does a capacitor hold? And finally, one professor was very annoyed at me and said, if you want to learn that, go to physics. And so it all came together, and I ended up in physics. Again, zero direction. It turns out that when I landed there, one of the professors said, you know, you're pretty good at physics. Maybe you should consider that as a major. And I said, I don't want to be a nuclear scientist. I don't know what that is. And he's like, no, that's not what physics is. Let me tell you. I've got friends that went to medicine. I've got friends that went into the markets. I have friends that, you know, became engineers, all sorts of things. So physics is a good foundation. And he convinced me that physics was actually a useful degree. And he was not incorrect. He was very correct. It turns out that I thrived in physics. I could ask all the whys, and somewhere in there was a first principles equation that one could derive and get a basic understanding in the world. But it turned out that I wasn't very good as an experimentalist. So most of the department at that HSI was experimental physics, lots of high energy physics and some materials like surface science. And I broke a very expensive piece of equipment, and then I decided I was no longer good at experimental physics, and also I didn't have the patience for it. I ended up transferring to a program at University of Florida in material science engineering, which was all computational. This is how I ended up in HPC, and this is how I ended up doing simulations. So I worked on a couple of problems. One was a theory problem. And then in my second year, my advisor changed my project again and ended up changing a project the third time. I ended up working in polymers. So first I was going to work on some covalently bound systems and like metal deposition and theory development. And then because that didn't get funded, my advisor was like, well, we're not going to work on that. We're going to work on polymers. So I had to go back to classes, took another 3 courses in polymers. I had no idea what a polymer was other than poly something, and had to learn all about polymers. And it turned out I was really good at it. And well, it just out of luck, a postdoc left at that point and went on for his first job at Samsung. And she pointed at me, she says, you're pretty good with computers. Why don't you manage our closet cluster? So this is circa 2006. Lots of closet clusters were, you know, common in many universities at that time, and it was literally what you think it is. It's a closet, a very small room that had very little AC power and had some computers that were just kind of piled on top of each other. So we had a whole bunch of Dell desktops that were clustered together, and I loved every bit of it, and I loved every bit of making people's applications run fast. I learned about parallel programming from a very wonderful man called Dr. Philpott over at University of Florida. And I was the queen of getting your application debugged, running fast. I could recompile kernels once I figured out how to do that. I could create all sorts of things, file systems, etc. And then in my third year, it was very clear that I was having a lot more fun doing this. I had automated my entire project in a series of scripts that would just run applications based on whatever I talked to with my advisor. And then at the end, I would show up on Thursday for our weekly meeting and be like, I got these results. And I was clearly not into the results as much as I was into, I tweaked the application, I made it faster, I made it better. Just around that time, some newfangled things called GPUs were coming out. And they were, the University of Illinois, John Stone over at University of Illinois was doing some really cool stuff with molecular dynamics, running out of GPUs using shaders. And then I told my advisor I wanted to do that. And she said, if you want to do that here, you're going to have to move to computer science. This is not what I'm doing. And then she also told me that computer GPUs were a fad. This is back in 2008. So I still want to meet her one day and remind her of that because it broke my heart that I was basically washed out of a PhD program when I was in the right all along. But it's okay. I'm still a little bitter. I'm not going to deny it. So I dropped out of my PhD program and I ended up working at an agricultural genomics company because they said all you need to do is know math libraries. I had no idea about agriculture. I'm a city girl and I had no idea about genomics. When I interviewed, they said, do you know anything about genomics? I said, ATCG, and they're like, you're hired, that's enough. And so I worked there for 3 years, built supercomputer for them. And then I went to a SC23 conference in Denver. No, it was Seattle or Portland. And then it turns out that they were hiring. And I just sat next to somebody, told them what I was working on. And they said, sounds like you'd be great. We've been trying to fill this position for about 8 months. And then that's where my career really took a turn for really big supercomputers. After that, I ended up working at NVIDIA. After 6 years at Oak Ridge National Lab, I got sucked into the world of, not gonna lie, money. It paid really well. And I loved being part of the early days of like AI at NVIDIA. So it was about 2018. And then after that, I did some consulting during COVID. I had a friend that was working with a lot of pharma companies. So I did that because I felt like that was something where I needed to do it. It was interesting. I worked with Pfizer and GSK and Takeda and Johnson & Johnson. All of those people were trying to find vaccines or trying to find therapeutics for COVID. And I felt really good. Spent a year there. Then somebody kind of poached me to go work at my first startup called Next Silicon, which is a hardware company. And I thought, you're throwing money at me and you're telling me I can be a director and I can build my own team. So I went to my friend who was the CEO of the consulting firm and I said, I wasn't looking, but this dropped in my lap. And he said, go for it. If it doesn't work out, come back. And then I got bit by the startup bug. I love being at startups. This is my second startup at Voltron Data. And it all comes back to everything that I've been having issues with all along in my career. It's basically how to get data from point A to point B, how to get data structured so that you can compute on it, how to get data to scale, how to get data integrated, all of those. That's probably the hardest part right now of anything that's been, with anything sort of analysis. And then on top of that, people want to do AI and you have all of these disparate data sources that exist in all sorts of places. So that's the short version of my career and everything else that I put in there. And everything else that I've been able to do. But what I want to do is give you an overview of what it means to scale and what it means to work with computers at scale. And because I don't know your background specifically, we're going to make this very, very informal, and so informal that I am not going to bore you with slides. We're going to do this. I'm going to draw on the screen. So I'm sharing my screen and hopefully that'll come up soon. Let's see.
Very bold of you.
I know. Feels like I'm unprepared, but I'm not.
No,
I've done this
that's
before,
awesome.
I swear. Okay, let's see. Can y'all see that?
Yeah, looks good.
Yes.
Great. Okay, so we're going to make this very, very informal. You can stop me at any time, raise your hand. I have two screens going on. I have an iPad that I'm drawing on and have another one that's a laptop that I'm actually looking at. And so you can stop me at any point and say, you just said a term, because, you know, sometimes we're in the field and the lingo just kind of flows and you forget to stop yourself and explain the lingo. So at any moment you can do that. You can also do that on the chat. And then if I miss a question on the chat, I'm sure that Jamie and Charlie and Dr. Hayden will help me out and flag me down and say, hey, Fernanda, you just said some weird lingo. You know, help us out here. What does that mean? So let's start with, what does it mean to scale? So the first thing you have is you have a computer, you know, like I have right now, right? This is your little keyboard, your screen. And what we want to do is we want to do some compute on it. So for those of us that are at least 30 years old, you probably remember the days where you had a computer and you go to the store and then it would say something like a computer has, you know, 4 cores. And this is like a little CPU with, you know, 4 cores in it. And then it would have something like, you know, this is 2 gigahertz speed. And for a long time, anywhere between the 90s, say the mid 90s, and about 2004-ish, most CPUs had a single core, and they were about 1 to 1 point something, maybe 1.2 gigahertz. And the way for you to do anything faster was to simply get one that was then at 1.3 gigahertz. So it was just, you know, take a new computer, take the application, and if you were doing any sort of compiled language, like I mentioned before, C++ or C, not an interpreted language, but even interpreted language, if you just ran it on this other computer, you would get faster. But at some point, the way to get faster became you need to get more computers together. So you would just kind of string these computers. And so the early days at Oak Ridge National Lab, sorry, wrong color. Early days of Oak Ridge National Lab, you would just take a bunch of computers and you just connect them via, you know, a network. And then you would then compute, and you would take your program and you take your data, and let's say you take your data like this, and you would break it up into 2 halves, and you say, you know, from I, you know, equals 0 to I equals 100 here, and then I equals 101 to I equals 200 here. And you would just do, you know, half of your data, and then you would start at a different point in your data. And hopefully those will finish at the same time and you wouldn't have any other issues that are too complicated for this short intro to HPC. But the way that this network was connected, in the early days, there were very many types of ways that you can do this. There were shared memory models, which is something that Cray used to do, basically make a really big computer seem like it has a really big memory that is encompassing the whole thing. But when folks got scrappy and cheap and started building those closet clusters, the way that you use was something that, if you haven't heard of it, the way that you communicated between these two computers is something called MPI. When computers got more cores, what people did, so let's say we have more cores now, and I'm going to put 4 cores in each of these computers, people just, instead of, say, using something else to do the computing within the computer, people just assumed that each of these cores was just a separate core. So now I went from 1 to 2 computers being separate, and then I would just do 1, 2, 3, 4, and I would run what's called ranks on these computers. So I would run MPI ranks on each computer, and people then did parallel computing and parallelize their applications and just assume that each of these cores were its own separate little CPU. And that worked for a little bit, and we went all the way up to 8 cores. And in fact, the first supercomputer that I met at Oak Ridge National Lab was a supercomputer called Jaguar. And that computer went from 2 cores to 4 cores to 8 cores to 16 cores. And each upgrade was, I think, about every 2 years or so. And applications would just, that used MPI would just how many cores do I have in this computer? Then I'm going to put this many number of ranks, and then how many cores do I have in the next computer? And so applications got really, really easy to scale in that sense if you had written it with this library that you'd be able to send messages together. In fact, MPI is it stands for message passing interface. And forgive my chicken scratch. So message passing interface is what MPI stands for. That's great.
Definitely not
but then,
chicken scratch. I gotta say, your writing on a tablet is impressive.
I appreciate that. So this is great. And then there was a supercomputer, and I'm going to make this supercomputer. Let me even make it a little bit bigger here. I'm going to make it blue because that was the color of this supercomputer. It's called Titan. And Titan was like this. It had, remember I said before, it had 2 CPUs essentially. A Jaguar had 2 CPUs. So let's draw back what Jaguar was over here. Jaguar had 2 CPUs and then some memory banks. And then a network card that would then move out. So network is red. We've established that already. So we're going to use red. So that was Jaguar, and then up to the end it had 16 cores. So 8 cores each. So this was 8 and this was 8. When Titan came along, what they did was they decided, you know what, we're going to remove a CPU. So essentially this CPU is gone. We're gonna put another CPU here that's 16. And then we're gonna put this newfangled thing called a GPU. And this is the thing that became a fad, if you remember from my earlier story. And GPUs were really different and yet not so different. So let's talk about what a GPU is. A GPU is the following. GPU, the one that we use was NVIDIA, so I'm going to use green because that's the color of NVIDIA. So a GPU's entire job is to determine on your screen what color this pixel should be. That is the job of a GPU. So this one is this, and this one is going to be pink. That's all a GPU does. And what you can do in a GPU, how it looks is different. So a CPU, we mentioned before, had, say, 4 cores. Let's keep it simple, 4 cores. These cores are really fancy. These cores can do things like, you know, you want to watch a cat video, and I don't know how to draw cats, and you want to do a word processing, you know, on the next one, and you want to do that at the same time. That's what these cores are for. They can do a lot of fancy functions. They have basically built-in functions that can do a lot of fancy work. But the problem is I don't, you know, for science, I need to add, right? A computer at the bottom of it, it can only do adding. And so all I need is to take, you know, 0.1 plus 0.2 times 0.3 and give me an answer, right? That's really all I want to do in a scientific application. And I have thousands, tens of thousands, hundreds of thousands of points. And turns out that this looks a lot more like what color should the pixel be, because what color should the pixel be has a lot to do with, like, you know, in a video game might have to do something, you might probably have heard it, like ray tracing. So like a color from a source might be coming here. Where's my yellow? I need a yellow sun. So speaking of sun, we just had an annular eclipse. So I have a source over here, and I need to determine after this then gets sort of, reflected off this surface, you know, what color is it going to be over here on this table? Well, maybe this color is going to be, say, a different shade of brown because this table is wood, but it's in the shade. That's all a GPU does, and that GPU has some fancy equation, f of x, that determines color. Well, f of x can be arbitrary, and I can program each of these cores arbitrarily for a different kind of f of x. Maybe it's not something like a color that I want to get at the end, an RGB value, right? So red, green, and blue value. What I want to get at the end is maybe pressure. Maybe I want to get at the end, I want to get something else like a force or an acceleration. So in the case of the work that I was doing, which is I've got a whole bunch of little atoms, right? So let's get a little water molecule over here. I need to get things like, what is the force between these things happening here? And then, you know, water is polar, so my equation might have some sort of electrostatic force here and some hydrogen bonding, right? And I want to be able to do this and loop over all of these molecules. So I've got, you know, molecule 1 is going to be a hydrogen. It's at XYZ position. And molecule, not molecule, atom. Atom 2 is another hydrogen. It's another XYZ position. And so on and so forth until 3. And I've got, I don't know, 300, let's say. I've got another oxygen XYZ position. And all I need to do is I say, hey, what is the force between 1 and 2? What is the force between, you know, 2 and 300? What's the force between, you know, 1 and 300? And I just need to loop over these two, these two loops. Basically, I have an outer loop and an inner loop, and I just go like, for molecule number 1, calculate all of the forces between, no, molecule, I keep saying that. Atom number 1, calculate all the forces with all of the atoms in this system. Atom number 2, calculate all the forces in the atom in the system. And you can get fancy and say, well, maybe I don't have to go too far. Or maybe there's a certain radius where the force doesn't really matter. It's too small, it doesn't feel it. But those are all sort of technical details of an algorithm. But essentially, I can just program each one of these GPU cores to do that force calculation. And it doesn't have to be very smart. It doesn't have to play a cat video and do your word processing. All it has to do is be very low powered, very dumb. And the early GPUs, what we're talking about here, these early CPUs in the mid 90s were about a gigahertz. We're talking, by the end, there were probably something like 3 gigahertz, 2.5. Actually, I think it was about 2.2 gigahertz. So these cores were running at 2.2 gigahertz. Here, Titan's little cores were running at best 700 megahertz. So they're slow. But I had 2,600 cores on a GPU. So it doesn't matter that they're slow, because in one clock cycle, essentially, I could do 2,600 points versus in a 16-core GPU, I would do essentially 16 points. Maybe if I do some fancy like hardware threading, maybe I do 32 points. But so I do 32 points really fast. Maybe I do it even 3 times as fast. So let's say we even do it 3 times as fast. Now we're talking about doing like 96 points, but still that's not 2,600 points. And that was a big game changer between CPUs and GPUs, is that I could do a lot of bandwidth, right? Or I can put a lot of data through this piece of hardware, and in the other end, with just essentially a few clock cycles over, I'd be done with 2,600 points, 2,600 points, 2,600 points. And as long as I could keep all of my data on this piece of hardware, and I wouldn't have to like leave the hardware for very long, because the communication was kind of slow, the way that it sat on the board were kind of slow. There are all sorts of like details in the optimization of this. As long as I kept the data there, I could just go through data the entire part. And so now we're talking about what do supercomputers look like. So in the era of Titan, we have a computer that has, a CPU, really, nice GPU, and then let's do memory blue, so some memory nodules in there, and then I've got a network. And Titan had this essentially, and this here, Titan had 18,688 of these. So we can get a lot of work done in 18,000, and going all the way to 18,000 nodes was actually really, really, really hard. There's a point at which the amount of data that you're passing through these messages actually overwhelms the amount of calculations that you're doing. In other words, it takes longer for you to communicate with all of the computers. Imagine, say, a simulation where you have lots and lots of atoms, right, in a box, right? And I break up this box into different parts, and I send this one here to one computer, and I send this one here to another computer. Here's a little pink side of this box, and I send this one here to another computer. Each one of these, if I wanted to say, hey, did this atom go to this box? That's a communication that I have to have with another computer. And if there's a lot of, say, a very energetic system and you've got atoms moving between boxes a lot, you are overwhelming the network with all of this communication, and not enough time is being spent actually doing computer. Remember, I said, as long as you sit with your data on one computer really close to the core, you'll be fine. But in reality, when you're trying to scale into big systems, this becomes overwhelming. But even then, what we couldn't do before in a smaller system was there are certain things that we couldn't even compute in a smaller system. So when I was going to grad school, the sort of like big deal at the time is one day we're going to have a 1,000,000 atom simulation. Today, that's laughable. We can do organelles. We can do entire cells that are actually really true to size and true to the complexity of a cellular system. We can do viruses. 10 years ago, like somebody came up with a simulation of the HIV capsid, outer shell of basically the HIV virus. And that was an amazing, simulation on its own. And we're talking about thousands of atoms, maybe millions of atoms in there. But back when I was going to grad school, I mean, my systems were probably hundreds of atoms. In fact, my advisor 10 years before had done entire calculations doing quantum chemistry on systems that were up to like 7 to 14 atoms, silicon atoms that were just arranged in different ways and just taking the energy. And at some point, she gives us that in a class, a quantum chemistry class. She gives us that as homework. We bring in the homework. It took us maybe like a week to hand back. And she's like, yeah, that took my entire PhD. What you guys were able to do today in a week's worth of homework was my entire PhD. And I just had to sit there and run simulations, and they would take months on end. And so things have gotten a lot better. And if you were an astrophysicist during the time of Titan, it was very exciting because you could simulate entire universes. You can see the things, for example, a resolution of something like, galaxy formation, which is, very, very difficult to do. You can even do supernova explosions. So that requires a lot of particles. And not just particles, but you have to sort of create this little tracer particles that then exit this supernova, and you're following these tracer particles to find out what's happening with the energy, what's happening with the explosion, what's happening with the heat and everything else that's going on in a simulation like that. And before, we couldn't even fit this on a laptop, or let alone a desktop, or let alone an SGI machine, let alone anything else. And even if this communication was overwhelming, this communication here was overwhelming systems, at least we could do the simulations. We can explode the supernova now. We couldn't do that before. So after Titan, I got involved in a project that was very interesting, which is called Coral. So Coral project, something that you could go and Google and see what it was all about. But Coral was this sort of multi-lab procurement process where we were trying to find machines that were different architectures. So one of the things that ended up worrying the Department of Energy in the United States is that we were very dependent on a single vendor to give us essentially hardware. And also, it used to be that the United States government would be able to sort of wave money around and be like, who wants to get this money? And all of the hardware vendors would be like, me, I'll do whatever you want, give us the money. But by this point, cloud is starting to come online. Their procurements are bigger than the Department of Energy can do alone. And it became less interesting for places like, HP and Dell and even Cray and IBM, especially IBM, to even bother with these smaller systems that were the DOE, and we were the premier systems in the world, but we were not at the same cache level that, say, Azure and Google and these hyperscalers at Facebook and all were actually shelling out for social media around 2012, 2013 timeframe. So we said, well, the way to do it is to pool our money. So Oak Ridge, which is the OR here of this bit, Argonne and Livermore got together and said, let's pool our money and let's procure 3 systems together. But the crux is these 3 systems, 2 of them have to be separate, and they have to be different than one another. And then the other one gets a pick of whatever one of the 2 is. So Livermore got a pick of whatever 2 that we picked up here. And so Oak Ridge began the process of creating what's called an RFP, a request for proposals. We put together the requirements. I had to help put the questions together and ask scientists, what do you think you're going to need for the future? And what was fun about that exercise is that nobody could predict what they wanted for the future. And I always joke that, if you had asked people in the 1800s, what kind of vehicle do you think is going to be in the future? They're going to say we're going to have faster horses. They would have never said cars. And often in seeing this, the responses coming out of these things was faster horses, not necessarily cars. But what we had is we had the advantage of having these essentially programs that we could see what the vendors were thinking about in their future of their hardware. And we could see that cars were coming, not faster horses. And so we put together all of these requirements and we said, here's what we want. We want, this kind of system that should be able to explode supernovas, that should be able to maybe simulate the entire Earth, because climate science is very important to us. We want to be able to simulate materials. We want to be able to do, this, it should have this amount of bandwidth. It should have this amount of network bandwidth and speed and this many cores on a CPU. And we kind of listed what we wanted in a wish list. And then vendors bid and said, okay, I can give you a system that's similar to that, but here are the caveats, right? Or and I know you said you wanted this, but the best we can do is, not X, but we can do Y, or maybe we can do better than X, we can do Z. And so we did this and we all got in a room together and we came up with the system. We chose the systems that were going to be a part of these 2 procurements. And the system that Oak Ridge chose was now one that had 2 CPUs, each with 10 cores, and they had a whole bunch of other hardware threads in there, but it had also 6 GPUs. Oh, my drawing is terrible. So just remember this is 6 GPUs. And then 2 CPUs. And now each CPU has 3 GPUs to deal with. And that's a lot. And they're sort of separated a little bit memory-wise. So it's faster to go here to here than it is to go here to here, in theory. And then NVIDIA came out with this special interlink that makes it basically about the same cost to go between CPU and CPU and CPU and GPU. And but the sort of weakness in this was in this intercommunication in the network. So what I'm showing here to you is the evolution of these systems for you to get an idea of the sorts of things you have to think about when you're doing HPC. You have to think about the speed at which you communicate, because sometimes, like I said, you're going to have atoms that are moving or tracers that are moving from one area of the system to another, and you have to do this kind of work, and you have to kind of keep track of this. And whether that's happening in between systems or in between GPUs or in between CPU and GPU or in between CPUs and CPU, you have to keep track of this. That is the job of the developer writing these applications, to keep track of this. And if it sounds horrible, it absolutely is. It is hard. So it used to be when I went to school, I could code an application just using MPI, and I did, and I created one myself, and I built it, and it worked great. But now you have to build these interdisciplinary teams, because it's so hard to keep track of all of these things. Because, like I said, NVIDIA built this special networking thing called NVLink that you can use to communicate in between them. You have a GPU driver here, so you have to know a bit about how to work with a GPU driver. You've got MPI here, you got to know how to work that. And then you've got, out of there, you've got an entire, for example, a file system. So here's a file system, and you got to figure that out. And on top of that, you've got, the things that run on a GPU. You've got math libraries here, and no one can be expert in all of these. Each of these requires specific domain expertise and expertise in each of these parts. And it's become harder and harder to run these applications on supercomputers, because now the specialization and the breakdown has gotten, more and more specialized. But fear not. Luckily for most of us, there are applications already that have been built and have been, essentially verified and vetted by many communities. So many communities have come together. For example, the climate community, they have their own set of applications that you can just pick up, get, download. And many of the centers within the DOE, say NERSC, Oak Ridge, one of my jobs at that point was actually taking these applications, compiling the applications, making them as performant as possible, and having them available just as a module that you can load on, and you can just bring your data, and as a module, just load that module, and then you run the application on the supercomputer. And my community in quantum chemistry and molecular dynamics have a whole set of applications that people run. A very famous one in quantum chemistry is called VASP. And a lot of work has gone into these sorts of applications to make sure that they do a good job, that they are able to use all of the hardware on HPC centers, and they're able to use not just that hardware, but remember I said this procurement was, 2 different machines. Well, this machine here ended up being an Intel machine. So this machine here became Summit. And this Intel machine became one called Aurora. And as part of the risk that created the Coral project, what they were trying to amortize risk in case, say, a vendor pulled out or a vendor did not deliver what they promised. This is exactly what ended up happening in the Intel case and Aurora case. They simply axed one of the products that were going to go into Aurora. So Aurora was supposed to come online in 2018. It is now yet not online in 2023. It'll likely go online in 2024 because the original hardware got axed, and then the second piece of hardware got delayed, and then now they're just now getting to the point where they're releasing that. And it's exactly what the Department of Energy feared, that if they put all their eggs in one basket, that vendor might do something like this, and the entire mission of the Department of Energy, whether it's open science, which is Oak Ridge and Argonne, and NERSC, or behind what we call behind the wall, which is nuclear materials, nuclear security, would be jeopardized by the whims or business decisions. Whims is negative, but the business decisions of a hardware vendor. And so Aurora had a very different kind of architecture initially. Initially, it looked a lot more like the original CPUs, just a lot more of these CPUs. We're talking probably about somewhat between, I think, 100 to 200 cores. I forget what the details were exactly, and it was called a Xeon Phi. And then later on, Intel said, you know what, this is not going to work. So now Intel is actually seeing, remember I said these things called GPUs are going to be a fad? Well, Intel is now developing their own GPU, and that's going into Aurora. So we've seen an evolution from CPUs for compute to GPUs for compute, essentially in the last decade. Where all of the vendors first started making fun of Oak Ridge for this weirdo computer that was built with GPUs, to now everybody going, you know what, these GPU things are actually pretty cool. This whole project with Titan is the reason why we have AI today. And this is not an overstatement at all. And I'll tell you why. Part of the projects I'm bringing a supercomputer online is that this is serial number 0. We're getting the first piece of hardware off the assembly line. And this piece of hardware requires software to be built for it. And so all of the math libraries that we've known in HPC, things like LAPACK and BLAS, which are linear algebra libraries, all of these libraries had to be ported to the GPUs. So Titan, this is me attempting to draw Titan with the cabinets. This supercomputer here built GPU-specific libraries. There were mathematical libraries. And then some folks at Google that would enter these competitions every year that have to do with AI and neural networks, one day substituted a CPU library for a GPU math library. And the graph of this neural net kind of looked like this every year. So this is like 1990 all the way to 2000, I think it was 2012, is really interesting because it kind of goes like this, kind of up, and then all of a sudden it goes boom. And this gap here was simply substituting a GPU library into this software framework that Google had built. And this was called ImageNet. And that began the, decade of classifying cat images on your phone and, seeing what images show up when you hit Google, Google Images, etc. And Titan was essentially what changed the game. And then NVIDIA was suddenly, they didn't plan for the AI revolution. It kind of fell on their laps because they were working in HPC. In fact, I had a chance to sit with Jensen upstairs. And if you ever go to NVIDIA headquarters, they have like a restaurant in the upstairs. And he sat down in like my first week of work there, which is very intimidating. And I said, how did you know the AI, AI was coming in the way that it was coming? He's like, I didn't. It just fell in my lap. We built these libraries and then people started using them. And then they pivoted toward AI. And all of the underlying math libraries that are running today and everything that we see in the frameworks of AI essentially came out of, little humble Titan that everyone made fun of back in 2012 when it was released as this one-off machine. I think we're at the hour mark, and I'm not sure how much time we have left to talk about data, but I think this gives you an overview of what HPC is, and I wanted to pause for a second and allow folks to ask questions.
Yeah, if anyone has any questions, feel free to unmute your mic and ask.
So the GPU is not only for graphic?
Correct. Today they're called general purpose GPUs, GPU. They are for compute. So you have essentially two kinds of products. You have a compute GPU. In fact, they don't even have the plugin for HDMI or anything else that would output any sort of image. It is strictly as a coprocessor that sits inside a node or even a desktop. I have, at my house, I have one that's called an A6000, and that one is just a coprocessor.
I have a question regarding using these machines with AI. Yeah, actually, you said in your presentation that's why we got the AI, because of this the advance in this type of technology. Yeah, so for the AI, actually, because AI need training to come up with a solution for a problem, we have to get the machine trained, get training first. So for any problem, my question actually, I wanted to, I don't know if you have the question as the answer for this, because from my understanding, the machine or the algorithm has to search the internet for data and has to download the data and get the training on this data and then come up with the models that can solve the problems, right? So yeah.
Go ahead, ask the last part.
So the machine here, how the code searches the internet, downloads the data that quickly and fast, and gets the training that fast, and then address the problem in our hand.
So this is a question that where the answer is multifaceted and nuanced and complicated. So let me start with, you don't have to train a large language model or any of the neural networks today on data that's based on the internet. In fact, there are lots of data brokers out there that are willing to sell you data that could be things like credit card data, taxi data. We often use in the examples that my team builds at Voltron Data, we use lots of data sets that are public data sets, things like Yelp, taxi, Uber, stuff like that. These people have provided these data sets. Netflix at one point provided data sets based on what people liked in movies and whatnot. So you don't have to go to the internet to do this. But for the ones that you see today that are creating images and they're spitting out information about the internet, I saw a piece of news this week where Stack Overflow is laying off people because essentially a lot of the stuff that's coming out of the ChatGPT has been trained on data from Stack Overflow. That's essentially bots downloading the data and using that data to train the large language models. And that can be very controversial, especially people that have created things like DALL-E, where it generates art that's been trained on essentially other artists' art without their permission. So we're not going to talk about whether or not that's ethical and any of that, but what people can do is they can simply go to a website and mine the website for the kind of data, download it to their cloud instance, and then create data sets. One way that you can create a data set is once you've downloaded the images, often what you have to do is you have to classify the image. So this is art, this is pictures, this is something. And sometimes the place where you're downloading from already has those things. So maybe you've tagged it, say in Flickr, or Instagram has been tagged with certain things. So maybe you can use another classifier that knows that this is a pet image and this is a person image and this is a building image. And it can go and it can do the tagging for you before you then use it to do some other kind of training with a specific end goal in mind. So you don't have to do that. And again, there are data brokers out there. So there are people whose entire purpose is essentially to download and offer it up to people that want to do it, to do the kind of training or a very specific kind of training. So again, this is a part of, I would like to go into the data part of it, but I'm not sure we're going to have enough time.
Thank you.
Any other questions, anyone?
Well,
So I personally loved it when you
Renata, would you speak to Voltron's interest in faculty, the faculty effort?
Yeah, so a few things that we're interested in. Number one is we are a global organization. We have about 130 plus people in over 20 countries. In fact, I have an employee in France. Out of my 4 employees, 1 is in France, 1 is in Zimbabwe, 1 is in the United States, actually 2 of them are in the United States. And I used to have an employee that was all the way out in Australia. So we're a global institution. AI is going to take all of us. So that's number 2. Number 3 is the data part. That is, the first question that came out of this was, how do people download the data and, get the data prepped for AI? That's what Voltron Data is looking at, where your data sits to where your data ends up being, either in analytics, ML, neural networks, AI, even scientific applications. That middle part is a lot of glue code that is very difficult to make sense of. And so when I was at NVIDIA, for example, I was working in the healthcare team, and I would walk into a place that had a lot of healthcare data, a lot of imaging data, and I'd say, hey, you're interested in AI, you called us over here for a meeting. Oh yeah, we have tons of data. And I was like, well, where does your data actually sit? I was like, oh no, we have tons of data. I was like, no, where does it physically sit? And they would tell me that it sat in 20 different databases all over the world, and goodness knows how many other file systems or file types. And none of it was harmonized. None of it was physically in a computable state. So they couldn't do AI, even though they were sitting in a massive amount of data. They couldn't do AI because a lot of it just sat in places that were completely inaccessible to it, and they would require a big team to just open up Python and create a connector that connects to this source and then brings down that to here, and then connects to that source and brings that down here. So what Voltron Data is trying to do, it's trying to build a unified system that can do that kind of work, number 1. And number 2 is we're trying to get people to use standards in this ecosystem of data. And where faculty come in is we're trying to seed curricula and help seed curricula to faculty. And then lastly, very proud of the fact that we're a very diverse team. I'm Brazilian, lots of Latin people. In fact, the merger between my CEO and another company, a lot of them came from Peru. It was a startup out of Peru. My CEO is Black. And so there's, out of the founders, there's not just a deep sense of responsibility that we have to be at the table, us who are not, majority white males, to be at the table to be able to create this next revolution. Otherwise, we're not going to be not only not part of it, but we might be, outright harmed by it. So by partnering with institutions that are training the next generation of, like HSI institutions, HPC institutions, we are ensuring that there is going to be enough of a pool of people that are going to be part of this next conversation. And so our interest in partnering with faculty is to help seed your curricula so that your students are ready for this next revolution, and we're able to then hire those students to come work for us. You're muted, Dr. Hayden.
So workforce development is a big interest for Voltron.
Huge interest for us, yes.
Thank you.
make one little note I really loved is when you mentioned all the machines that you've dealt with, Summit, Titan, Aurora, you said met. I love that. You met these machines. So that was really cool.
I actually have I think I've managed to get 15 pictures of supercomputers. Every time I went to a place that had a supercomputer, I made sure to ask somebody, can I stand in front of it and take a picture with it? And it started out to send it to my dad, and it just kind of became a thing. My dad passed away almost 10 years ago, and it continues to be a thing. So every time I'm next to a supercomputer anywhere near it, I ask somebody to take a picture next to it.
Come visit us over at TAC. So
I will look forward to it. I can't wait to see Frontera.
Okay.
and another question for you. So I know you've done a lot of I'm going to assume that you didn't really, you touched on this briefly, but you've done a lot of training sets, I assume, or built training data sets for some AI ML DL applications. How much, let's say the entire project is 100% of time, how much of that project time is devoted to cleaning up and setting up and organizing the data?
Yeah, the joke is that it's 85 to 90% of the time. The training part is only computer time, and then the inference part is actually the smallest amount of time. Inference is what you do after you've done all the training and you're trying to actually figure it out. It depends too on the kinds of data. So when I was working at the lab, we were working with something called the SEER databases. So every state that's signed up for this database is joined together with other states in the United States, and they take in reportable diseases. So if you get cancer, if you get now COVID, if you get HIV, all of these things are reported to this database as a way for essentially governments to keep track so they can make decisions later on say funding or decisions on things like clean water, et cetera. So if you are a part of a state, for example, there was an example in Kentucky where all of a sudden there was a hotspot of people getting a particular kind of leukemia. And it turned out that there was a leak in some industry or somewhere that was being dumped into the groundwater, and all of a sudden there was a spike of leukemia. Well, the data that was coming out they weren't able to analyze the data for 2 to 3 to 4 years. So if you see a spike in leukemia and you're only seeing it 4 years later, and that's taking a toll on your Medicare, Medicaid workforce, right? That's something that the state it's already too late, right? These people have already been contaminated. You can't try to figure it out. You can't ameliorate it. That you might be a decade before you can reverse the effects of what happened. And of course, people have been harmed along the way. And so the project was to simply take all of this data, that a lot of it was handwritten by doctors and submitted, and there weren't enough people to actually submit it into the database to just do like OCR, so optical character recognition, optical recognition of the actual page, and then use a neural network to figure out, okay, this is a cancer, diagnosis, this is stage 3, and then essentially extract the information out of that. And that project, we were able to get what was called gold standard data. And even in the gold standard data, there were duplicates, there were errors, there was even there, it wasn't something that was completely cleaned up. And we spent a good portion of the first 2 years actually going through each one of the things to create a good training data set so we could use that to train the model, and then use that model to use part of the data set that we didn't use to validate our model. And then after that, we were able to use it and put it into practice as part of this project. And that was just a whole bunch of Python scripts upon Python scripts and many, many eyes on the data just to get it to train. Things are getting better, but what Voltron Data is hoping to do is that we're hoping to not have to create all this glue code to connect to different kinds of databases or anything like that, and training and training people how to use database. Like Kentucky had a different database from North Carolina, which had a different database altogether from California. So just the actual physical like SQL language and how to communicate with those databases was completely different in all these three. So one of the projects that we are contributing to is called Project IBIS, and that is a Python open source framework that has 17 plus, I think 18 plus backends that you can just write Python and it does a translation and connects to that backend and gets the data you need.
Very cool. And I'm sorry, does anybody else have any questions?
Yeah, actually, I want to have one question here. I don't know. It's regarding your area of expertise, because you're starting actually looking at your background, all what you are presenting regarding the machine architecture and hardware. But now you're starting talking about data analysis, AI, image processing and stuff. So which area, which expertise, your background?
Like I said in the beginning of it,
Hardware and the machine architecture and stuff, or AI and data analysis and stuff.
So in HPC, it's hard. The reason why I got into hardware in HPC, number one, is because I've always been a nerd and I like taking things apart, to the horror of my mother coming home every night to like entire pieces of equipment that she spent a lot of money on being completely pulled apart. So that's the one thing. But in HPC, I had to do training. I was in charge of training, and I started running hackathons at Oak Ridge National Lab, training people how to use the hardware. And it required some domain knowledge in the hardware, and I became very interested in that. I ended up serving committees that had to do with hardware, and a lot of it has to do with how you get performance, has to do with where your data sits. And most people are thinking about the algorithm, but not necessarily the algorithm in the context of where your data sits. So think about that as if I don't know, do you cook? Do you enjoy cooking in your kitchen? Think about that in the sense of like, where do you put the knives? Where do you put the spices? Right? They have to be accessible while you cook. Otherwise, it's going to take a very long time for you to make that dinner. The refrigerator needs to be near it. And you have to have all of the ingredients ready to go. Otherwise, you're going to burn the bottom of your rice, right? You don't want to necessarily burn the bottom of your rice unless you're making Persian rice, and then it's a different kind of burn. But you don't want to burn the bottom of your rice. And so all of those things have to be accessible to you. And computing is very similar to that. You have to make sure that your data is staged in the right place at the right time. And it's done so in a way so it's not thrashing all over the system. So for example, if I have to, let me draw something really quick here. If I have some piece of data, and let's say this is an int, this is a float, and this is another float. And they're different. Maybe this is a float 16, maybe this is a float 64. If I'm going to do compute in a bunch of, darn it, if I'm going to do compute and in just the int part, the last thing I want is for me to get my memory cursor and the int to have to read through each of these boxes before I get my int, and then read through each of these boxes to get my int. What I want to do maybe is, if I'm going to do compute just on the int part, I want to get all the ints together. And so that when I loop over ints, I just go 1, 2, 3, 4, 5, 6, 7. They're all one after the other. And often when we're writing algorithms, we're not thinking of memory layout. And that's the biggest penalty you get is when this happens here, when you're trying to get pieces of data to then do your compute, is the fact that you have to traverse the memory, and it's very slow. And so I had to understand, what does it mean to do memory layout? What does it mean to stage in different kinds of memory? And in a computer that has a GPU, you've got the main memory, and you've got the CPU memory, and you've got the GPU memory, and you've got the network memory. Some network cards now have some bit of staging, and sometimes it can communicate directly, sometimes it can't. And all of these things come into play, and you have to know something about the hardware so that you can organize your algorithm a little better. And in the early days especially, there wasn't a lot of ways, the compilers just weren't that smart to do that for you, so you had to do it by hand. And so I was teaching people how to do that by hand, and then eventually compilers got smart enough and they figured out that they can do a lot of fancy things to move things around. But in the early days, it was very, very primitive. In the early days of GPUs, it was very primitive to get to the point where you can do compute in a very, quick, logical way without just thinking about algorithm.
Yeah, absolutely agree with you because I am teaching hardware and computer architecture, and also beside my background in artificial intelligence and computer vision. Yeah. Thank you so much. I appreciate it.
You're very welcome.
Amy, you look like you're itching to ask something.
Not this time. Actually, Fernanda has done a phenomenal job of breaking it down. I was worried about the question I was going to ask you about was actually regarding GPUs, because of course you kept using that, and I want to make sure people knew the difference between them, especially with the different types of new like DPUs and everything else that are coming out in the future. But someone else actually asked it, you answered it, so I left it alone. What
Yeah, I
I'm
thought I
surprised
saw
about,
you
I didn't know
up there.
how much experience you had in physics, and I also really appreciated you saying, you know, what led you to where you are and the person you are now. Because I was also the person that took stuff apart, and you know, at first you can't put it back together, and then you start getting better at putting things back together, and then stuff you break, you're able to fix, and then all of a sudden you find yourself in a role that you had no expectations of being. and I can't speak for you, but for me, getting involved in the HPC community, when I went to my first supercomputing conference, it changed my world, because I didn't know that world existed. And so, yeah,
I'm just a
thoroughly.
kid from Brazil. I had no clue that supercomputers existed, nor that I should apply. Like, all along my career, I just had a series of people who said things to me and believed in me. And there's one piece of advice my mom gave me is, don't tell them you can't do it. Let them tell you that you can't do it. You apply for it, and let them tell you no. And so I have, and I've gotten lucky with every time. And the last thing I'll say is, you know, when I went to Florida International University, I used to, you know, the prestigious university was the private university called University of Miami. And we were the public, you know, commuter university. And I used to look down at my, you know, my degree. In fact, when somebody asked me, where'd you go to undergrad? I was like, oh, I went to this university in South Florida. And they go like, oh, University of Miami. I was like, no, it's called FIU. FI what? And so I jokingly called it FIU because people didn't know where FIU was. And we were like 8 miles apart. And what was interesting is later on, I found out that every one of us that came out of that physics department, which back then had maybe 8 faculty, and today has like 30 something, 40 faculty. There was like literally 4 or 5 of us sitting in class, going through physics courses. Like, there was not a full class. I got an excellent education because there was the beginning of a graduate program there. And so all the faculty that was trying to do R1 level, you know, research and get their grants, and all of us were just really raw undergraduates. So I got to build like a pulse laser deposition system, and I got to do all of this like that. And all of these things in a bigger university would have been done by postdocs and advanced grad students. And I was doing it in my junior year. And every time I talk about it to other people, I'm like, you did what? And I was like, yeah, I was doing that in like my junior year of class. And then I went to this like biophysics lab and I worked, and I was like dissecting like house eyes, looking for zeaxanthin in the back, because they were doing research on like macular degeneration. And I was like, and people are like, you did what? And I was like, yeah, that. And today I realized what an excellent education I got. And what was funny about it is that we had all these professors from really great universities because they all wanted to be in Miami. I didn't know that. So I got an excellent education. We had people from Duke, we had people from Princeton, we had people from Berkeley, we had all sorts of, I had no idea. And here I'm thinking like, oh, I just went to this like kind of, you know, little university, a tiny little physics department, you know, I don't know. So when I got to the national lab, and I'm answering tickets from, you know, the sorts of places that I would have never applied to, MIT and Stanford and all of these places, I could answer all their questions. So, you know, little old me from Brazil that ended up going to little FIU and a little tiny department was answering questions from people in Stanford. And 90% of those questions is, let me Google that for you. And at least I knew how to Google. So I felt pretty good about my education. Looking back today and looking back at my cohort, the 10 of us that went through that cohort in those years, all of us have done very well. And we got an excellent education. So I don't know. I'm a huge fan of the little tiny departments because the experience you get is incomparable to a large place. I would have been a no one. In fact, I was when I went to University of Florida. First class I had in grad school was stadium seating, 300 kids in class. And I was completely lost. Like, I was lost in the shuffle. I had to beg for professor time to ask questions.
Right.
Well,
Any other questions?
I hope that faculty realize the caliber of mentors that are available to you this year, this hearing, from Fernanda tonight. And I think that we have an excellent group of mentors, and they're with a wealth of knowledge and background and experience that they're willing to share their time and share with you. So great job tonight, Fernanda, and we look forward to your work with these faculty members.
I'm looking forward to what everyone's gonna, create and present.
Yeah.
It's absolutely incredible. Thank you so much. Everyone, let's give a virtual applause to Fernanda. Thank you so much for joining us. Thank you so much for your effort. I gotta say, that was one hell of an origin story. So
Yeah.
I'm gonna steal the share back here. All right, so we have a few more things on the agenda. Let me just run through that really quick. Well, we've got it coming up tomorrow. So tomorrow, same time, same channel, we are going to do a overview on SGX3. Perhaps we might just jump right into the HPC Ed as a training resource. And we're going to do kind of a little bit of a crowdsourced mini hack during the training resource tomorrow. So everybody come, drink your orange juice, get totally creative, and let's see what we can do with this. So, and then after that, Thursday is our kickoff for our hackathon, if I'm not mistaken, and then see where you all go and see what ideas come out. Looking forward to it all. Once again, thank you so much, Fernanda, for that great overview on HPC. Not just the history of HPC, but how we're using it today and the evolution of HPC. And of course, your tremendous backstory. So thank you so much, everyone, for joining. Yes, Jamie?
Wait. Before people disappear, we're going to stop the recording here in a moment. And we really want to get a picture of everyone if we can.
Yes.
I hope we haven't lost anyone. So if you could take a moment and
stop.